Features of the model. Section 2. The Big Bang Theory offers a comprehensive explanation for a broad range of observed phenomena, including the abundance of the light elements, the CMB, large-scale structure, and Hubble's law. The theory depends on two major assumptions: the universality of physical laws and the cosmological principle. The universality of physical laws is one of the underlying principles of the theory of relativity. The cosmological principle states that on large scales, the universe is homogeneous and isotropic, appearing the same in all directions regardless of location. These ideas were initially taken as postulates. I didn't say that right. But later efforts were made to test each of them. For example, the first observation has been tested by observations showing that large possible deviations of a fine structure constant over much of the age of the universe is over 10 to the negative fifth power. Also, general relativity has passed stringent tests on the scale of the solar system and binary stars. The large-scale universe appears isotropic as viewed from Earth. If it is indeed isotropic, the cosmological principle can be derived from the simpler Copernic principle, which states that there is no preferred or special observer or vantage point. To this end, the cosmological principle has been confirmed to a level of 10 to the negative fifth via observations of the temperature of the CMB and the scale of the CMB horizon. The universe has been measured to be homogeneous within the upper bound of the order of 10% in homogeneity as of 1995. Expansion of space. Main articles: Friedman/Lamartre, Robertson/Walker metric, and the expansion of the universe. The expansion of the universe was inferred from early 20th century astronomical observations and is an essential ingredient of the Big Bang Theory. Mathematically, general relativity describes space-time by a metric which determines the distances that separate nearby points. The points, which can be galaxies, stars, or other objects, are specified using a coordinate chart or grid that is laid down over all space-time. The cosmological principle implies that the metric should be homogeneous and isotropic on large scales, which uniquely singles out the Friedman-Lamartre/Robertson-Walker FLRW metric. This metric contains a scale factor which describes how the size of the universe changes with time. This enables a convenient choice of a coordinate system to be made, called co-moving coordinates. In this coordinate system, the grid expands along with the universe, and objects that are only moving because of the expansion of the universe remain at fixed points on the grid. While their coordinate distance, co-moving distance, remains constant, the physical distance between two such co-moving points expands proportionally with the scale factor of the universe. The Big Bang is not an explosion of matter moving outwards to fill an empty universe. Instead, space itself expands with time everywhere and increases the physical distances between co-moving points. In other words, the Big Bang is not an explosion in space, but rather an explosion of space. Because of the FLRW metric assumes a uniform distribution of mass and energy, it applies to our universe only on large scales. Local concentrations of matter such as our galaxy do not necessarily expand with the same speed as the whole universe. Horizons. Main article: Cosmological horizon. An important feature of the Big Bang spacetime is the presence of particle horizons. Since the universe has a finite age and light travels at a finite speed, there may be events in the past whose light has not yet had time to reach us. This places a limit or a past horizon on the most distant objects that can be observed. Conversely, because space is expanding and more distant objects are receding ever more quickly, light emitted by us today may never catch up to very distant objects. This defines a future horizon, which limits the events in the future that will be able to influence. The presence of either type of horizon depends on the details of the FLRW model that describes our universe. Our understanding of the universe, back to our very early times, suggests that there is a past horizon. though in practice our view is also limited by the opacity of the universe at early times. So our view cannot extend further backwards in times, though the horizon recedes in space. If the expansion of the universe if the expansion of the universe continues to accelerate, there is a future horizon as well. Thermalization. Some processes in the early universe occurred too slowly compared to the expansion rate of the universe to reach approximate thermodynamic equilibrium. Others were fast enough to reach thermalization. The parameter usually used to find out whether a process is very early in the universe has reached thermal equilibrium is the ratio between the rate of the process, usually rate of collisions between particles, and the Hubble parameter. The larger the ratio, the more time particles had to thermalize before they were too far away from each other.